All right. Good morning, Algebra 2.
Good morning.
Yay. All right. So, to start things off today, we're going to have a fun little puzzle, like a game or an activity to help wake you up, right? Yeah, it's this stuff. So, here's our little activity. It's going to be so much fun. I've got two numbers. Look at like each row. Like there's a C and then a B and then the solution. And those are different numbers, which you can see, obviously. I don't need to say that. But anyways, here's your task. Your solution for each of these needs to be two numbers that multiply to C. So times, if you multiply two numbers together, it equals the number in column C. But when you add those same two numbers, it equals that number in column B. Now this first row is pretty easy because what are the only two numbers that multiply together to equal 7? 7 and 1. If I add those together, do I get 8? Yes. So our solution here is a 1 and a 7, or 7 and 1. Order doesn't matter. This isn't a coordinate. I'm just making a list of the numbers, okay? Now, what about in the second column? There's a 10 and a negative 11. Can you think of two numbers that we multiply to get a 10, a positive 10? If they're both negative, that works, right? A negative 10 and a negative 1. Because if I multiply those, I'd get a positive 10 because a negative times a negative is positive. But if you add them up, it would be a negative 11. Exactly. So do you see the activity here? You see what we're doing? All right, go ahead and fill out the rest of this chart. Don't worry, there's more. Oh, I guess not that much more, but there's some more. All right, so try doing these next 5. And don't worry, there's a reason for this in our lesson today.
Pretty sure.
They're all possible. Everyone. Well, yeah. Negative 90 and 1. Anyone think about that? Two numbers that multiply to negative 90? Since this multiplies to a negative number, that means one has to be positive and one has to be negative. And so if you add those numbers, it's really like you're going to be subtracting the two numbers in a way. And so if I have a positive 10 and a negative 9, if I add those together, don't I get 1? Yep. How about negative 12 and 4? Any ideas?
Hold on. That is 6 and negative 2.
6 and negative 2? Yeah, that definitely works. 6 comma negative 2, because 6 minus 2 is a positive 4. If it were a negative 6, positive 2, that'd be a negative 4. It's a different number, right? Different combination. 9 and negative 10.
Negative 9, negative 1.
Is he right? That works, doesn't it? Negative 9, negative 1. Yeah, that adds up to a negative 10. This one should be pretty easy. 64 and 16. 8 and 8, right? 8 times 8. Then 8 plus 8.
Oh, yeah.
Yeah, that's it. Finally, negative 24 and 2. This is a thinker.
That is 6 and negative 4.
Does that work? Positive 6, negative 4. 6 comma negative 4. You multiply them, you get negative 24. You add them, you get 2. That's it. Was that pretty easy?
Yeah.
Good, because doing that process is the quintessential skill for factoring. You might remember the term factoring from Algebra 1. And basically, factoring is going to be our first technique or first way or next way. There's several ways we're going to learn on how to solve a quadratic equation. Dun, dun, dun. Now, there's the quadratic formula. There's factoring. There's completing the square. We're going to use all these different techniques. Today's lesson is going to be how to solve quadratics by factoring them. All right? So remember, this whole Unit 5 is all on quadratics. A quadratic equation in standard form. Remember in our last lesson, our lesson earlier on, we did vertex form, like from the graph and by completing the square. The other form that we look at is called standard form. This is a more traditional way of writing a quadratic equation. The general way we write this is ax squared plus bx plus c, using those coefficients a, b, and c. A, b, and c are going to be actual numbers. They're not going to be represented with letters. Only the x would stay a letter in the final equation. And there's a quadratic term. That's the one that has x squared, right? And that exponent of 2 is what makes this equation a quadratic equation. If it weren't x squared, it would just be like a linear function. The term that's just an x by itself without an exponent, that's called the linear term. You can think of, if I just look at that second part, if it were just that bx plus c, doesn't that kind of seem like mx plus b? Remember, like the slope of a line? So that'd just be the linear term, that's the linear piece. And then we know c is always our constant. And we've had that often this year, right? The number by itself at the end, we always call the constant. It doesn't have a variable. It never varies. It never changes. It always stays the same. You gonna do some jumping jacks to warm up? Wait, why are you cold? We already warmed up. Yes, that was epic. Let's just move on. All right, so what I want you to do for this first piece is to identify A, B, and C. What's A, what's B, and what's C in this equation? But wait a minute, that's not written the way that I just showed you, standard form. So can we go ahead and write this in standard form really quickly? All right. Am I allowed to just distribute this 2 to each of those, right? That is x squared minus 4 squared. We can do that, right? No. Good. I'm glad that you're defying me so vehemently. That's right. We need to write this as an x minus 4. And since it's being squared, that means it's being multiplied by a whole another x minus 4. And we have to do that distributing. X times x is x squared. X times negative 4 is negative 4x. Then distribute the negative 4. Gives you negative 4x. The negative 4 times negative 4 is positive 16. Combine like terms. X squared minus 8x plus 16. Okay, now our function's in standard form. Now we can identify A, B, and C. In this function right here in blue, what is A? What's the value of A? Ah, very good. A is in front of the squared term. That's part of the quadratic term. What's B? That's A. B is 8 or negative 8? The negative would come with it, right? Because I could write this middle term as plus negative 8. Like the standard form is technically all pluses. That's actually, but adding a negative 8 is the same as subtracting 8. And what's C? 16, positive 16. Everyone good about identifying A, B, and C? We feel confident with that? All right, I wish that were all to it and I could just test you on identifying A, B, and C, but there's a little bit more we have to do. That would be kind of nice. But we're good enough. We can handle more than this. For sure. First off, you only really need the part that's in the box. Everything else is kind of summary of stuff you kind of know. For example, you know that a quadratic is called a parabola, right? It's that U-shaped graph. We've already worked with that. We know the peak, which is either going to be the maximum or the minimum based on if it opens upwards or downwards, right? That peak of the parabola is called the vertex. Again, you know this already. We did that from the graphs H and K. But here's the new part. The x-intercepts. Now, we talked about intercepts before when we were graphing lines back at the beginning of the year. And an x-intercept is the point where our graph crosses the x-axis, which is the horizontal axis. Now, because a parabola is U-shaped, how many x-intercepts could we have? Will we have just one x-intercept, do you think? So if this is our coordinate plane, if I have a parabola, how many times does that cross the x-axis? Twice, right? When it goes down, it crosses the x-axis there. but it also crosses it over here, right? So a parabola has two x-intercepts typically. And these intercepts have a bunch of different names that you're going to see in different textbooks. Different math teachers will use all these different terms, but that's what it's referring to. Sometimes they're called the zeros of the function or the roots of the function. And so that's why I want you to write down this key information box right here. These words are all the same thing when we're referring to a quadratic equation. If I ask you what's the solution of the quadratic equation, I'm ultimately asking you, where would this parabola cross the x-axis? What are the x-intercepts? They're sometimes called the roots of the function or the zeros of the function. So anytime you hear any one of those, just know that it's the same thing. Zeros, roots, x-intercepts, solutions. They all mean the same thing. And just based on the little, my picture right here, hopefully you can see that. Okay, this is what we're talking about. The parts of the parabola where it crosses the x-axis. That's what we're referring to. So again, how many x-intercepts does a parabola typically have? 2. Will it always have 2, do you think? Dun, dun, dun. Oh,
You're saying that it can't be more than 2.
Can't be more than 2. Could there be less than 2?
Yeah.
Yeah, absolutely. So here are 3 different scenarios. When we're solving a quadratic equation, we won't always get 2 solutions. Over on the far right, yeah, it's going to cross it 2 times. But what if the vertex is right on the x-axis? If it doesn't like pass through the x-axis, what if it just bounces off of it? You can think of. There's only one point of this parabola that's actually on the x-axis. That'll happen sometimes. So sometimes we're going to get only one solution. Other times, look at this parabola. How many times does that parabola cross the x-axis? Doesn't. Do you think it's just because I don't see enough of the graph? Like, will this line eventually like curve back down and hit the x-axis somewhere over here? Do parabolas do that? No. It's going to be going up forever and ever and ever, right? So this will never come back down. Now it's never going to come down on the left or the right. So there will never be a solution. Like, it's never going to be an x-intercept sometimes. Those are the only 3 possibilities. Parabola or a quadratic equation will have 0, 1, or 2 solutions. And this is an excellent visual for helping you kind of conceptualize or remember the different possibilities. You're just sliding it up and down. Now, same thing could be if it were upside down. You could have the same thing, right? Like that parabola also has 0 solutions. This parabola would have, 1 solution, and then another parabola could have 2 solutions if we're opening downwards. Any questions so far about this? So these next few lessons are all about solving a quadratic equation, meaning we're trying to find those x-intercepts. And we want to find out what are those values. Where does it cross the x-axis? All right, so just to familiarize yourself with that terminology, imagine if I give you a graph of a parabola, and I said, hey, tell me the solution of the quadratic. Well, what's the solution of this quadratic here? First off, how many solutions are there?
2.
There are 2. What are those 2 solutions? How'd you get -3 and 1 so quickly? It's as easy as that, everybody. That's your solution, -3 and 1. Pretty cool? This is the equation. That's the solution to, well, technically, if this were a 0, that's what's going on. Let me explain that a little better. So this is the equation of the parabola. And these x-intercepts, these are points, right? Like this point here is 1, 0. The point over here is -3, 0, right? Because it's on a grid. What do those 2 points have in common? They both end in 0. What is that number called? The second number in a coordinate is the y coordinate. Isn't every point on the x-axis going to have a y coordinate of 0? Because you're not moving up or down at all. They all have a y of 0. So the idea or the concept that we're going to use to solve quadratic equations is simply go to the actual function itself And if I want to figure out what the x-intercept is, what number should I plug in for y? What number is y going to be for every x-intercept? It's going to be a 0. So what we're going to do is say, okay, well then 0 equals x squared plus 2x plus 3. I'm replacing the y with a 0 because I know that every x-intercept is going to have a y coordinate of 0. So let's just plug in a 0 for y and see, hey, what does x have to be? What does x have to be to make this entire equation true, to make the left side equal the right side? And that's how we're going to be solving it. There's a bunch of different techniques to figure this out. So for all these problems, we're going to start by setting y equal to 0. 0 equals, then the rest of the quadratic. Because we know that these intercepts will always have a y coordinate of 0. Hey, do you remember just like 2 slides ago when I asked you to write down all the different words for the solutions of a quadratic equation? Do you remember what one of them was?
0.
Haha. The zeros of a solution. Do you understand now why they're called the zeros of a solution of a quadratic? Because you plug in a 0 for y. So they're sometimes called the zeros of the function. They're the values for x that make the equation equal to 0. Pretty cool, right? Now, typically, we're not going to have a graph. It's not going to be as easy as just pointing to the 2 parts where my line crosses another line. So for today's lesson, we're going to learn how to solve these quadratic equations by factoring, using a technique called factoring, and then applying something called the zero product property. Ooh, that sounds fancy. It's pretty simple. This zero product property, I've got a fun little equation down here. A times B equals 0. Now, I don't know what A is. I don't know what B is. But if I multiply A times B and I get a 0, what do you absolutely know that either A or B has to equal? One of them has to be a 0, right? Because if A and B are 2 non-zero numbers, I'm not going to get a 0. The only way to get a 0 when you're multiplying is if one. Could both of the numbers be a 0? Yeah, 0 times 0 would also be 0. But I know at least one of them has to be a 0. So using this concept, we're going to try to rewrite these quadratic equations so that I get one value times another value equal to 0. And if we get our equation written in that form, we know that one of two things is going to happen. Either A must equal a 0, or B must equal a 0. And then we just solve both of those pieces, the 2 parts that are being multiplied together, solve each of those separately for x, and those will be our 2 x-intercepts. Let me show you what I mean. Do you see how I've got one binomial being multiplied, right? If they're right next to each other, it means multiplication. It's being multiplied by a second binomial, and that product is a 0. This is essentially saying A times B equals 0. It's a terrible equal sign. Right? One thing times another thing equals 0. Well, if the product of these 2 binomials is 0, that tells me that one of 2 things must be true. Either the binomial on the left, this 2x plus 5, so either this has to equal a 0, right? That whole piece on the left is 0, because if this is a 0, I don't care what I'm multiplying it by. 0 times anything is still 0. Or the other piece, the x minus 8, either that factor must be a 0 for the same logic, because anything times 0 is going to be 0. So I know that those are our 2 possibilities. Either that first binomial on the left is a 0, or the binomial on the right is a 0. So we write 2 separate problems. And do you think you all could solve those 2 equations for x pretty easily? Yeah, go ahead and do that real quick. It's okay if you get fractions. Just leave it as a fraction. I'll give you 5 more seconds.
I'm supposed to give you everything.
You what?
I'm supposed to give you everything.
You finished?
I know.
So to solve it for x, I mean, like in this green one, if I want to get x by itself, what I cancel out first? Yeah, subtract 5 from both sides, so you get 2x equals -5. Then what's our last step? Just divide by 2. So we know that x could equal -5 over 2. Over in blue, well, that one's even easier. How do I get the x by itself? Just to add 8. What does x equal? +8. So these are our two solutions for the quadratic equation. If we were to graph that original problem, it's going to be a parabola. And see, -5 over 2, that's -2.5. So I could say on my graph, if I go left 2.5 units, I'm going to have an intercept. Or x could equal 8. So if I go right 8 units, I'm going to have another intercept. I know my parabola has to cross through those lines. Wow. Isn't that amazing? For those of you watching from home, everyone in the class was like just jumping for joy with excitement about this. They thought it was the coolest thing in the world in the last 2 minutes. All right. So here's the official process that we're going to use to solve a quadratic equation by factoring. I would suggest jotting down these 5 steps to use for your easy reference when practicing. When you practice these steps over and over enough times, like on a, say, homework assignment, I bet you're going to learn this really well. So to solve a quadratic equation by factoring, I'd like you to jot down these 5 steps in your notebook for you to refer to while working on these assignments or these types of problems. So write it in standard form. Remember, that's like y equals ax squared plus bx plus c. So rearrange all the terms so that they're all on one side. Set equal to 0, that just means replacing the y with a 0. I mean, it's barely even a step, but we should make sure we put that in there. 0 equals ax squared plus bx plus c. Step 3 is what we're going to work on today. That's the main skill that we're going to have to practice today, factoring. And factoring means we're going to break this down into typically 2 smaller factors, right? A factor is just something that multiplies into another thing. Like, remember we made factor trees for simplifying radicals? Like if I had the square root of 48, you would break that down in a factor tree. Like, what's 2 numbers multiply to give you 48? Same thing. These are factors because they multiply together to equal this larger trinomial. And then once you've got those 2 factors, right, these are just being multiplied together, you set each one of those factors equal to 0. So you'd say either this first binomial equals 0, or the second. It's not always a binomial. It could be a monomial sometimes. You set each of those factors equal to 0, then solve them both for x. So you'll see, hey, x equals this number, and this x equals that number. And solving them, that's just using your basic algebra, canceling things out, moving things to the other side of the equal sign until the x is all by itself. Let's try some of these together. So write this down. F of x equals x squared minus 12x plus 27. And we're going to go through those 5 steps together, okay? So to begin, we want to write this in standard form. But is that in standard form already?
Yep.
Yeah, ax squared plus bx plus c, we're good to go. Step 2 says set it equal to 0. All that means is instead of writing f of x or y, we're just going to make that a 0. X squared minus 12x plus 27. Typically, whenever you're rearranging these terms to be in standard form, you're going to have a 0 on the other side anyways. So just make sure that it's equal to 0. Now here is the skill for today. We need to factor this, meaning I want to break down this trinomial into 2 smaller factors that if I were to multiply those factors together, think of like if we were to FOIL, like first, outer, and last, all that jazz. If I were to multiply these 2 together, it would equal this up here. Now we could guess and check, but there's a better way to do that. And that way is based off of our warm-up that I had you start off today with. Do you remember how I labeled those columns C and B in standard form? Isn't this known as B and this term known as C? Right? AX squared plus BX plus C. So to factor it, you need to play that same little game that you did during your warm-up. Can you think of 2 numbers that multiply to C and add to B? So multiply to C, but they have to add to B. 2 numbers that multiply to 27 and add to negative 12. Negative 9, negative 3. That works, doesn't it? So because those are our 2 magic numbers that make this work, a negative 9 and a negative 3, that's the second part of each of these binomials. The thing that goes in front is just x. X minus 9 and x minus 3. So it's going to always be that x and then following whatever those numbers are. As for, is it going to be a plus or a minus inside? Well, that depends on whatever your 2 numbers are that multiply to C and add to B. And this is factored now. Pretty easy, right? And by the way, the reason we use x and x is because this first term is x squared. And if we were to multiply, think like when I distribute, don't I do x times x first? That gets us x squared. So that's what that's all about. All right, so that was the factoring step. Now to finish solving it, remember, this is not the solution. The solution are the actual values of x. What number can I plug in for x to make this true? Well, now we want to set up 2 smaller mini algebra problems. These are being multiplied together. These are my 2 factors. Set each factor equal to 0 separately. So either the x minus 9 equals a 0, or the x minus 3 factor could equal a 0. And to solve these, well, you could all do this in your sleep, right? To get that x by itself on the left, you got a negative 9, just add 9. X equals a 9. Over on the right, add a 3 and x equals 3. It's as simple as that. What do you think? Pretty cool?
Yeah.
Normally, once you get to this step, you'll start taking a shortcut of just realizing, oh, I just kind of flipped the sign of that term, right? The opposite of a negative 9 is a positive 9. Because you're asking, hey, what number could I plug in for x to make this whole factor a 0? Well, what number minus 9 is a 0? Hey, a positive 9. And that's what our solution was, one of them. Okay? Pretty groovy. All right, I'd like you to try this one now. Oh my goodness. So 4x squared plus 24 equals negative 20x. What do you think we should do first? Oh, yeah, we could divide by 4. Now, my steps always said, get it in standard form first. So I'd get everything to one side, that ax squared plus bx plus c. Let's write it like that first, but then I like what you're saying. So let's see, if I just add 20x, add 20x, that'll give us 4x squared plus 20x plus 24 equals 0. Is this standard form now? Yeah, is it okay that the 0 is on the right instead of on the left? Does that matter at all? No, that's fine. Now, normally we've got this set equal to 0 already. That was step 2. And step 3 would be to factor it in those two parentheses. But there's this number in front. That makes it trickier because it's not just going to be an x times x to give us x squared, because it's got to equal 4x squared. So if there ever is a number in front of your x squared, we want to get rid of it, we'll just divide by that number, right? That's the opposite of multiplying. However, you're probably going to only want to do this if every single term is divisible by 4. Otherwise, you're going to have a fraction, and we know how scary those can be to work with. In this case, does every term divide by 4 nicely? Even that last one, can I take 0 divided by 4? Yes, we can. 0 divided by anything is 0. It's the reciprocal of that we couldn't do, right? I couldn't take 4 divided by 0. That can't happen. But 0 divided by anything is 0. So let's just rewrite this now as x squared plus 5x plus 6 equals 0. Now, can you factor that pretty easily? Now be careful with this. There's a couple different possibilities. There are a few things that students typically think is the correct factored form of this, but it's not quite right. Remember that the numbers have to multiply to C and add to B. So what two numbers multiply to 6 and add to 5? And he says 2 and 3. Does that work? Yeah, it does. So I'm going to write this as x plus 2 and x plus 3. Yeah, that works. Then my solution, again, I could take the time to set each of those equal to 0 separately, but when it's this basic, I know that this just means, hey, x is going to equal a negative 2, right? I'm just flipping the sign of that factor. And also x is going to equal a negative 3. So that's my solution. And again, we could plug these back into the original problem to check. But for these problems, we're not going to get extraneous solutions. So let's just trust our algebra for now. Unless you have time on the test to go back, then you could do that. Questions on how I got any of those pieces? Or are we feeling okay? Yep. Awesome. All right, now we've got some different scenarios for factoring that we're going to go over. 4 different factoring techniques, all right? Typically, those examples that I just went over, that's your standard factoring, sometimes called reverse FOIL, what multiplies to C and adds to B. That's the nicest, most common one that you're going to see. But there are 4 other types of factoring that we're going to go over now. These first 2 special types of factoring are used when we have only 2 terms. This first technique is called the GCF, which stands for, does anybody remember? Good, greatest common factor. So the greatest common factor means you look at all the terms, right? Look at this term and this term, and you're thinking, hey, what do both of those terms have in common? Or specifically, which factors do they have? Or what could I divide both of those terms by? How about a 5? Are they both divisible by 5? Yeah, they are. What else are they both divisible by? What else do they both have in common? Yeah, an x. Don't they both have at least one x available? Right, the first one's got two x's, the second one's got one x, so they both have an x in common as well. So the GCF of this, we could write it as 5x. Then in parentheses, I'm going to rewrite those same two terms, but after I divided out the GCF. So looking at that first term, 5x squared, if I divide out the 5x, what would I be left with? Just an x by itself. And 20x, if I divide that by 5x, what do we get? A 4. I gotcha. Now, a good way to check that you did this right is think, hey, if I were to distribute this in, would it go back up to this original form? Does that work, everybody? Yeah, so the GCF, another way to think about it is reverse distributing. Okay, instead of distributing something in to multiply, what can I divide out and leave out in front? Typically, we don't do that. Normally, we always distribute to multiply things together, but this is the opposite. I want to break things down into separate, smaller pieces, because once I've done that, well, now in green, even though I don't have two sets of parentheses like on the earlier problems, I still have two factors. It's just my first factor is just a 5x. This factor is being multiplied by the x plus 4. It's still two things. It's still a times b equals 0. So I'm still going to set each of those factors equal to 0 and solve for them separately. But this first one on the left is just going to be a little bit different. So either that 5x could equal to 0, or the x plus 4 could equal to 0. Right? Those are our two factors that when I multiply those two together, we get that original problem of the 5x squared plus 20x. Now on the left, to solve 5x equals 0 for x, what's it going to equal? Just a 0, right? 5 times what number is a 0? Well, x has to be a 0. And again, we could just divide both sides by 5, and 0 divided by 5 is 0. So I know that 0 is one solution. On the other side, just subtract 4. And so we see that, hey, x equals 0, or x could equal a negative 4. And back up in our original problem, we can see that, hey, both those numbers would actually work, right? If x were a 0, this would cancel out. If that were 0, that's a 0, and you get 0 plus 0 is 0. If it were negative 4 squared is 16. 5 times 16 is a bigger number. I don't know off the top of my head. It works, don't worry. Y'all can work on that on your own free time when you're bored. Second type of factoring with only two terms. All right, so always try to factor with the GCF first. Is there a common factor I can divide out in front? Kind of like the one where you noticed that there was a 4 that it could divide out of all those terms. That was great. That's going to make our numbers smaller, easier to work with. Or that previous one where you just factored out a 5x from both terms. In this one, though, we've got x squared minus 36 equals 0.
Square root. No, can't. Only the negatives thrown out.
I like that you saw that you could take a square root of that, right? 36 is a special number, isn't it? Yeah, what's up? All right, so we kind of recognize that, hey, 36 is a perfect square, right? Isn't that 6 times 6? So it looks kind of special, like we could solve it. But this is a special case. It's got a name called the difference of squares. Now, the word difference is the same word we use for subtraction. First off, are we subtracting here? Yes, we are. So that's why we use the word difference. Of squares, this is referring to perfect squares. Well, we already know that 36 is a perfect square because that's 6 times 6. What about x squared? Is that a perfect square? Like, could I take the square root of x squared nicely? Yeah. What is the square root of x squared? Just x, right? So these are two perfect squares, and we're subtracting them. It's literally the difference of squares, right? Now, we can't use GCF because x squared and 36 don't have any common factors. But because they're perfect squares and they're being subtracted, we can break this down into two conjugates. Ooh. Remember the word conjugate? We use that when we're rationalizing denominators. It's like the same two terms, but one's a plus and one's a minus. So when you factor the difference of squares, you're going to get two conjugates. So one's going to be plus, one's minus. And guess what the actual like values are on the left and right? It's just the square roots of each of those terms. So what's the square root of x squared, you said? What's the square root of 36? 6. That's how you factor the difference of squares. X plus 6, x minus 6. Pretty groovy, right? And remember, when you multiply conjugates, those middle terms cancel out. It's the same thing as if you just multiplied the first terms together, which is x squared, and the last terms together, which would give you a negative 36. So it is the opposite of multiplying conjugates. Now, this isn't quite the solution yet, but I bet you can figure out pretty easily what would x have to equal to make this equation true. Yeah, you just flip the signs. Opposite of a negative 6 or a positive 6 is a negative 6. Opposite of a negative 6 is a positive 6. All right, so that's the difference of squares. So look for that perfect square that you recognized. And be like, oh, wait, something special, something easy here. I can take a little shortcut. All right, that's 2 of the 4 special cases. These both deal with 2 terms in our quadratic. This next method is when we have 4 terms. Ooh, so jot that down. If you've got 4 terms in your quadratic, then we're going to use a method called factor by grouping. So go ahead and jot down 2x squared minus 8x plus 3x minus 12. It's equal to 0 already. Now, do all 4 of those terms have a GCF? No, that's not going to work. And we could, but I want to show you this technique because it's important for our last factoring method, okay? It's a pretty simple idea for factoring by grouping when you have 4 terms. All we're going to do is make 2 groups. You're just going to group up the first 2 terms together, and then we're going to group up the second 2 terms together. Okay, just like I did, keep the sign with each term. Notice how I've kept that plus sign with the 3x there. So you group up the first 2 terms, and you group up the second 2 terms. Now, looking at just that first grouping, the 2x squared minus 8x, did those 2 terms have a GCF? They do. What do those 2 terms have in common that I could kind of divide out in front? A 2 and an x. So I'm going to make this 2x. And what would I be left with in parentheses after I divided out that GCF? X minus 4. So if I took a negative 8x divided by 2x, I'd get a negative 4. How about the term on the right, the group on the right, that positive 3x minus 12? Did those two have a GCF? A 3 and 12, they both have a 3, a positive 3, correct? So I'm going to divide out a positive 3 out in front. Then, in parentheses, what would we be left over with after dividing both of those terms by 3? An x and a negative 4. All right, what do you notice now at our equation? The parentheses are the same, right? So since these parentheses are the same, if I viewed this as one term and this is a second term, what do they both have in common? They both have an x minus 4. So x minus 4, whatever that like parenthesis that you're left over with, it should always be the same when you use factor by grouping. That is one of your factors. Anybody want to guess as to what the second factor is going to be? Yeah. Look at what we divided out in front, the GCF. Here we had a 2x. Here we had a plus 3. Well, that's the only other stuff we have in the equation. 2x plus 3, that becomes our second factor. Yeah, it's like I divided the x minus 4 out in front. What I was left with is just a 2x plus 3. So that's factoring by grouping. It's like magic the way that works. Math magic, because I'm a mathematician. I'll stop. Now we're not quite done. We would still have to set each of these equal to 0 and solve for x. Now this first one, what's the opposite of a negative 4? A positive 4. This one over here, though, the 2x plus 3, it's going to be a fraction. So you subtract 3, right? What's the opposite of a positive 3? Negative 3. What's the opposite of multiplying by 2? Dividing by 2. And so this second one is going to be negative 3 over 2. And again, if you're not sure where I got that from, just set 2x plus 3 equal to 0 and solve that for x, and you'll get negative 3 over 2. Then these are our two solutions to this quadratic equation. Those are our x-intercepts. If we were to graph this parabola, it would cross the x-axis at those two values. Any questions up to this point? Because those were all the easy techniques. I saved the best for last. Oh, there he is. That's Mr. Paston.
Carlos, you okay?
Everybody good? Ready to rock and roll?
Raise your hand if you're all right.
All right, so here it is. Last skill of the day of factoring. It's called 5-step factoring. Guess how many steps we have?
5, 2,
Oof.
6.
Sometimes I want to cry after hearing some of these guesses. So write this quadratic down. 7x squared plus 16x plus 4 equals 0. So first off, there are 3 terms. So I can't use GCF. There is no GCF, right? Those 3 terms, they don't have any common factors. Difference of squares? Nope, it's not subtraction, not perfect squares. Factor by grouping. Can I do that? Nope, there's only 3 terms. If there were 4 terms, we'd be in business, but there's only 3. And Actually,
No, because there's not one X.
well, what if you separate it into two terms, both with an x?
Then when it comes back together, then it's 16X squared.
No, because if you're adding two terms with x, they don't multiply. It'd still be a regular x. It's a good idea. Frank's saying, hey, what if we made it like plus something x plus another something x that added up to the 16? Then we would have four terms. That's a great idea. As a matter of fact, that is what we're actually going to do. That was amazing. So yeah, essentially, we're going to have to use factor by grouping, but we need to get four terms instead of three. So I want to split this 16 up into two different terms, both with an x. Okay, but these could be anything. Imagine all the numbers that add up to 16x. Well, I could have 10x and 6x. I could have 15x and 1x. Or I could use subtraction, right? I could have 20x minus 4x. There's literally an infinite combination. So how do I pick the correct combination that I know will definitely work? Take A, the leading coefficient, and C, the constant, and multiply those together. What do you get? 28. Now, play our favorite factoring game. Pick two numbers that multiply to 28 that also add to 16. So I need two numbers that multiply to 28 and add to 16.
14 and 2.
Does 14 and 2 work, everybody? It does. So what we're going to do, since 14 and 2 multiply to 28 and add to 16, I'm basically going to rewrite this plus 16x as plus 14x and a plus 2x. Because if I add those together, won't that still be equal to 16x? That's not changing anything, right? Like that's still the same value. It's still 16x. I'm just writing it as two separate terms. Now the term in front, that 7x squared, stays put, and the term at the end, that plus 4, stays put. All we're doing is separating that middle term into two smaller terms. This is a plus sign. Multiply to 28, add to 16. Now, looking at our equation, how many terms do we have? We have four terms, so which factoring technique can we use now? That factor by grouping. I group the first two terms together, and I group the last two terms together. We then pull out the GCF from each of those two groupings. The first grouping is a 7x squared plus 14x. Well, what do those two terms have in common? Yeah, a 7 and an x. So this first grouping, I'm dividing out a 7x. And what would that leave us with? X plus 2. Okay, the second group we had was a 2x plus 4. What's the GCF? What's a 2x and 4 have in common? A 2, a positive 2. So we write a plus 2, and then a set of parentheses afterwards. What would be left in the parentheses after dividing each of those terms by 2? X plus 2. All right, do a quick check at this point. Do our two sets of parentheses match? Are they both x plus 2's? That's right. So we're going to write x plus 2 as one of our factors. What's our second factor going to be? Awesome. Just the leftover stuff, the GCFs that we had divided out, the 7x and the plus 2. And we write it as 7x plus 2, just like that. Remember, our final step is to simply set each of those equal to 0 and solve for x. So what does x equal for this first term? Yeah, just flip the sign. Opposite of a positive 2 is a negative 2. How about for that second factor? What would x have to equal to make that a 0? Good. Negative 2 over 7. And that's our solution. X could equal a negative 2 or a negative 2/7. Those are also the x-intercepts of our parabola. If we were to graph it, it would cross the x-axis at both those points. And just a reminder, any of you who are unsure how we got negative 2/7, well, just write this factor equal to 0. Subtract 2 from both sides. Divide by 7. And you get negative 2/7. So what do you think about the most difficult technique today? Is it really that crazy bad? No, it's not. It's not too crazy. Works out pretty well. And I mean, if Frank came up with that idea on his own, someone said it has to be easy, but I don't know. Maybe he's a secret genius. So yeah, the key first step to this, everybody, is multiplying the first term and the last term together, and then playing our little factor game like we started off today with in that warm-up. What multiplies to the product and adds to that middle term. And those will be exactly how you want to separate that middle term, that b, to make sure that you're going to be able to factor by grouping. Easy, right? Okay, so those 4 special cases that I just showed you, you're going to practice each one right now. All right, so I've got 4 examples left, and that's it for today. So 6x squared plus 9x equals 0.
Wait, are they in order like this one?
Yeah, there's the first one. So it's using that first technique again. There's only 2 terms. So the 2 terms was either the GCF or the difference of squares. Which one do you think this is? Yeah, it's not the difference because it's not subtraction, and they're not perfect squares. 9 is, but the 6 isn't. So GCF, what do those 2 terms have in common? And it's a 3 and an x. Make sure you divide that x out also because they both are x terms. Once I divide 3x out in front, what are we left with?
X plus 3.
What's 6 divided by 3, though?
2x.
Yeah, 2x plus 3. 2x plus 3 equals 0. All right, so that's the factored form. What are my solutions? What does x have to equal? 0 and negative 3 over 2. Awesome. Write this first factor. 3 times what equals 0? Well, 3 times 0 is 0. So 0 is one solution. Again, I can get that just by setting 3x equal to 0. I've just divided both sides by 3 and x equals 0. Second part, 2x plus 3. Flip the sign. Divide by the coefficient. Negative 3 over 2. Okay, that's factoring by dividing out the GCF. Pretty groovy?
Real. So you're really feeling the word groovy today.
Is it? How many times have I used it?
Like 4.
4? No
At
way.
least 3.
I've never used groovy 4 times a day. Well, I guess I just used it now for the 4th time.
Oh, there's 4.
How many times do you think I'm going to hit it before the end of class?
5.
5? 5 more or just 1 more?
Just 1 more.
I'm going to try not to.
I mean, if we got some groovy stuff.
Ah! I almost said it again. Look at this funky problem. Oh, I am. So example 7 is 4x squared minus 100 equals 0. So look at your previous techniques. There's only 2 terms. It's subtraction. And what do you notice that's special about the numbers 4 and 100? They're both what kind of numbers?
Perfect squares.
They are perfect squares. And it's subtraction. So is this the difference of squares? For sure.
That's real. Root.
Now you're using the word too often. I'm not going to say it.
Oh, that's such real. I couldn't help myself.
All right, so to factor the difference of squares, you take the same two terms, but one's going to be a plus, one's going to be a minus. Now what goes into those number spots? All you do is take the square root of each side. So like, what's the square root of 4x squared? Very good. So I know it's going to have a 2x plus, then a 2x minus. What's the square root of 100? So I do a plus 10, and this will be a minus 10. And those are your two factors. Now, this isn't the solution yet. Again, remember, we're solving by factoring. So we factored it to make it easy to solve. Our final solution will be x equals a negative 10 over 2 and a positive 10 over 2. Yeah. Can I simplify each of those fractions further? 10 divided by 2, it's 5. So x equals a negative 5 and a positive 5. By the way, if you feel like saving some ink, if it's the same two numbers but one's positive and one's negative, you'll typically see this fancy sign in mathematics. Plus minus. It's called a plus minus sign. Any idea why?
Plus and minus.
Oh yeah, I see that now. Cool. All right, so x is a positive 5 or a negative 5. We have 2 left, and then we're done. Are we ready? Example 8. Ooh. Good luck. This problem is really crazy. 30x. Oh, wait a minute. Hold up. For sure. 30x squared. Oh, that's embarrassing. Must be the first time I've made a mistake all year, right? That's a joke. Making mistakes is good. That's how we learn. There's 4 terms. So I bet I'm going to use factor by grouping. All right, keep working through it. Look at those earlier examples where we used factor by grouping. And try to repeat that process. I'll give you another like 30 seconds. Don't stress out if you're still working. That's fine. But I see some of you finishing up. Okay, let's take a look at this one together. 4 terms. I group up the first 2 and the last 2. Looking at those first 2 terms, what is the GCF? Very good. A 10 and an x. Once I divide out the GCF from those 2 terms, what would we have remaining inside the parentheses? 3x and a -1. Yeah, make sure you keep that -1 there. Sometimes when students divide something by itself, like 10x over 10x, you're like, oh, it goes away. Because sometimes we do cancel stuff out that way when we don't write it. But in this case, that -1 is super important. Because if it weren't there, if I distributed in a 10x, I'd only have a 30x squared. There wouldn't be that second term. So you need to have that 1 there. Very important. All right, now look at the second grouping. 6x minus 2. What's the GCF? Positive 2. And what would that leave us in the parentheses? 3x minus 1. Gee, where have I seen that before? Hey! It's like magic how that works.
It's
Pretty good, great. Almost got me. So 1 factor is 3x minus 1. What's our second factor? You take just those 2 GCFs and you make a binomial out of those 2. So 10x plus 2. Make that a little bit better. 10x plus 2. Okay, so we've got our 2 factors right there. We set each one of those equal to 0 and solve. What's our first factor going to be? Positive 1 divided by 3. Just divide it by the coefficient of x. Our second one, what do we get? I heard a negative 2 over 10. I also heard a negative 1/5. Can be simplified, can't it? Yep. That's negative 1 over 5. So it'd be negative 1/5 and 1/3 right there are our 2 solutions. Pretty groovy, right?
Yeah.
I wanted to say it, then I stopped and paused. And I'm like, I have to. Ooh, 6 times? That'd be nuts. Tell you what, you finish this problem on your own, and I don't know, do a groovy little dance, a jig, if you will. But you have 3 seconds. Oh, just kidding. Tell you what, I'll give you 10 seconds because that's how fast some of you are finishing your Delta Math. What? In case you didn't guess, you're going to need to use 5-step factoring on this one. What? Because the x squared term has an 8 in front of it. So there's no GCF. It's not the difference of squares. There aren't 2 numbers that, if I think out 2 numbers that multiply negative 3 and add to 2, I still have to take this 8 into account. And so we have to use 5-step factoring. Take the first term times the last term. What's 8 times negative 3? And so we're going to use that negative 24 just temporarily to figure out how we should split up that middle term. This is a little bit different because that's a negative 24, meaning I'm going to have one positive number and one negative number. So it's not necessarily 2 numbers that add to 2x, but it's going to be 2 numbers that, well, if I subtract one from the other, two numbers whose difference is a 2. 4 and 6, which one's positive, which one's negative, though? Since it has to add to a positive 2, the bigger number is going to be positive as well. So I'm going to make this middle term plus 6x minus 4x, because I know 6x minus 4x is the same thing as 2x, right? If I combine those like terms, I'd still get a 2x. That 8x squared goes in front, the minus 3 stays at the end. This is equal to 0. So that first step was just getting 4 terms. So we can now use factor by grouping. What's that? It's a good point. This one is a little different. 8x squared and 6x, do those two terms have a GCF? Good. A 2x. What's that leave us with inside the parentheses? 4x plus 3. Now look at that second one. 4x and 3, or negative 4x and a negative 3, they don't have any common factors, except there is one number that is divisible by every single number in the world. What can you always divide every number by? A 1, in this case, a negative 1. And so, to me, I'm looking at this 4x plus 3, and don't you kind of know that we're going to want our two factors to be the same, right? That's how these factor by grouping problems always work. The two parentheses are the same. So I'm thinking, well, I know that this is going to need to become a 4x plus 3. Right now, it's a negative 4x minus 3. So whenever they're the same already, like without taking out GCF, think about dividing out a 1. In this case, since they're both negative and they both need to be positive, I'm going to divide out a negative 1. Because dividing out the negative 1 is going to turn this into a positive 4x plus 3. Now, are those two factors in the parentheses the same? For sure. We know one factor is 4x plus 3. And the important part here is looking at those other two GCF terms. It's not just a 2x, but it's going to be a 2x, yeah, the minus 1. 2x minus 1. And that's the important piece right there. Because if you didn't have that minus 1, it'd just be a 2x. And if we had multiplied those together, it'd be just a binomial instead of a trinomial for that original problem. Final solutions. X equals positive 1/2 and negative 3/4. All right. It seemed to me like you all caught on to this factoring pretty quickly. Does that seem right? You all feel pretty comfortable with it? So I just want to make sure you understand the distinction between understanding a concept, as most of you seem to do right now, and learning it. So don't think that just because you followed this lesson really well and all these examples really well, that you've truly learned this. Think about, could you do this problem again in 3 weeks without practicing it? With your notes. All right. Imagine if you had a test, say let's call it a final exam, sometime in the next month, some random date. And you think if you don't look at this again, do you think you'd be able to do all these steps exactly again? Oh my gosh. Why would it be on a final exam? But do you see the point I'm trying to make? What do you need to make sure you do? Study and do your homework, right? Homework at a minimum, just to practice this. Because that feeling that you have right now, wouldn't it be awesome if when you took a test, you felt the way you did when working through these example problems? How cool would that be? You can do that by just practicing 15 minutes a night. I don't think that's a huge ask. That's less than a TV show episode, all right? Right? It is. And just by practicing a handful of these, even if it's on a day when you didn't have class, that I didn't assign a new homework, you can still just practice some of them. Practice some of the older ones, right? Delta math, it just regenerates new problems. You're like, oh, I was kind of rusty on that skill. And you can be like, oh, wait, I know that target 4.2 and 4.3 are coming up on my next test again in 1 week. Maybe I should practice those some more before next week. Yeah, you can do that. Yeah, we have a test next week. Really, actually, would I lie to you? Where can we go to check, see if we have anything coming up?
The haiku calendar.
Oh, for the year.
I think I saw it one time. I don't know.
Look at that. You hit calendar. Oh my gosh. Does it really? Test number 5? What happens if I click on it? Because I want to know what's on the test. Oh my gosh. It tells me exactly what's on the test. That seems like cheating, doesn't it? Like I'm telling you, hey, this is what's on your test next week. It's like you could practice this stuff before next week and do really, really well on the test. Whoa, that's insane. Do it. I want everybody to get 3s across the board.
And then you're gonna do your little groovy dance for it.
And then I'll do a groovy dance. All right, everybody. So jump on to some Delta Math. We've got about 13 minutes remaining, but you can knock off at least half of your homework right here, right now, while things are still fresh in your brain. Do the rest of it later on tonight to make sure it's mastered and that you've truly learned it. Good luck. Have fun. I'll talk to you soon.